Hello everybody, welcome to Planets and Moons Chat. It's, what is it, the 16th of November, I think, 2017 now. I'm Dave Rothery, Professor of Planetary Geosciences here at the Open University. I'm speaking to you from the Open STEM laboratories, and I'm going to be talking to you about planets and moons and answering your questions. Please look at the screen below. There are widgets there. We'd like to know where you're from, wanted to know what your favourite moon is, tell us what you're studying, and there's a Who Wants to Be a Millionaire question. Some of you are already answering that. That's great, I'll give you the answers at the end. Now, I chair S283, the Level 2 Planetary Science course, and I also run the Moons MOOC, so welcome to you, whichever of those you're from, and we've invited other people as well, so hello everybody. With me today is my special guest, Professor Monica Grady, who is the genius behind the Orion course. What do we call the MOOC?
Orion MOOC. I can't remember. It's just got, well, I just call it the Orion MOOC.
But it's starting in January.
Am I allowed to correct you?
Yes.
It's the 15th of November today, not the 16th.
So it is.
Before everybody starts to write in. Yeah, the Orion MOOC. That's going to be starting in January, when we've got nice clear skies, nice cold winter nights for everybody to get out there and look at Orion. You don't need a telescope. Camera would be nice.
Yeah, it's a popular MOOC, not quite as good as the Moon's MOOC, but nearly so.
Well,
and it only runs for 4 weeks.
It is. It's 4 weeks. It's a very short MOOC. It's an introduction to astronomy, so it's one of those things to introduce you to stars and planets as well as moons.
Yeah, I think a lot of people on the Moon's MOOC came to us via the Orion MOOC. So, Monica, before we get on to answering the questions, which is the main purpose of this evening, Monica, what are you working on lately so people know who you are?
Right. Well, I work on the origin and evolution of the solar system on a daily basis. So that keeps me gainfully employed. What I'm working on at the moment, or have been working on recently, is comets. If you remember the fantastic Rosetta mission,
I remember it landing very well, Monica.
And the Philae lander for November 2014, 3 years ago. It doesn't seem like 2 minutes.
Here it is on the screen.
And there's a picture of Comet 67P Churyumov-Gerasimenko, and the Philae lander, which was carried by the Rosetta mission, landed on the front face. It didn't land quite where it should have done, which is a real shame, but there you go. And my involvement with the Rosetta mission is as a scientific advisor to the Ptolemy team. Now, Ptolemy is a shoebox-sized bit of equipment, which was designed and built at the Open University. And we've got the prototype, which is about the size of, a small cupboard, and it was shrunk down. And what it does is it measured the gas and the species trapped in the ice on the comet. And I'm helping the team interpret their results and trying to understand what they actually mean.
So what's the story about the water from comets? This water doesn't quite match Earth's ocean water. Is that still the story?
Yes, it is. One of the reasons for going to the comet was to find out where did the Earth's oceans come from. So if you think about what the Earth was like 4,568 million years ago, so a few million years, right at the beginning, the dawn of time for the solar system, it was incandescently hot, really, really hot. The whole of the surface was molten, and so a lot of the volatiles, the water, carbon dioxide, sulfur, was all boiled away. But of course, we know that there's plenty of water on the Earth at the moment. Yeah. As I came over to this lab, it's pouring with rain. A bit icy as well. So we've got plenty of water. So where's that come from? Now, the idea is that it's being brought to the Earth by comets, by asteroids hitting the Earth all through time. And so we can measure the water in the sea, water in the rivers, water that comes out of our taps, the rainwater, and we get an idea of its signature in terms of the hydrogen and the heavy hydrogen, so hydrogen to deuterium. And we measured the hydrogen to deuterium ratio in the comet, and we sort of know what it is in the sun, and we know what it is in Jupiter, and it's like they all ought to add up to the same sort of number. But you can't say, right, comet plus Jupiter equals Earth, because Jupiter is more or less what we think the pre-solar nebula was.
Yeah.
So if it started off with Jupiter and it went in this way to the Earth, I'm talking about the hydrogen in the water now, and this way to comets, you ought to be able to add the two together, and it doesn't work. So it's like, that's a mystery. So what does that mean? It means we're going to have another mission to go to a comet.
Are comets likely to be very diverse in their isotopic compositions? Would that be how you'd explain away the fact that this comet doesn't match the Earth? Or?
Yeah, I mean, one of the things is that we've only measured the one comet, 67P, to that high precision. There have been other measurements of water on other comets done by remote measurements from the Earth and from remotely from other spacecraft. And they've all got big error bars on them. Yeah. And what it shows at the moment is that every comet is different. They sort of cluster a little bit into one family, and they're not, but they're not, it's not as if we've got two types of comets, long period ones and short period ones, and they don't seem to have values of hydrogen which clusters according to those. So yeah, it's still a mystery.
More missions. But you don't just do comets, you do meteorites as well.
I do meteorites, which are bits from asteroids, or mostly the meteorites are from asteroids. But we have a small group of meteorites that come from Mars, and one of the ones that I'm particularly interested at the moment is a meteorite from Mars. And I think we'll get the picture up. Yes, there it is. So that picture is in three parts. The top bit labelled A is the outside of this meteorite, and you see it's really black and shiny. It looks as if it's been painted with enamel paint. And what that is that's the fusion crust, so that's where it's heated and then quenched as it's come through the atmosphere. The heat doesn't transfer inwards, it all radiates outwards, so it doesn't melt as it comes through the atmosphere. The second picture, or the second part of figure A, is a cut surface of this rock, so you can see what it looks like on the inside. And then the bottom half, the bit labelled B, with the scale bar right at the bottom right-hand corner, which it says 100 microns, that is a picture of a close-up of the cut surface.
So that's about, 2 millimetres across, maybe?
Something like that.
So that's a breccia, yeah?
It's a breccia. All right,
looks like it's from the moon, not Mars.
Well, I'm afraid it's from Mars, because the oxygen isotopes show it's from Mars. The gases trapped in it show it's from Mars. It's definitely from Mars. It's definitely not from the moon. And what's really exciting about it, as you just said, is it's a breccia, and it's the first Martian meteorite that has been recognised as a breccia. We've got 100 or so meteorites that have come from Mars on Earth, and they're all igneous, and this is the first one that has shown to be something that has been broken up and reassembled. And the question is, what sort of breccia is it? Because there are three different types of breccias. You can have an impact breccia, so something comes and hits the surface of Mars, and bits get all mixed up. Yeah. You can have an igneous breccia, of sort of stuff that's come out of a volcano and got bits sort of mixed in with it. Or you can have a sedimentary breccia, where you've had like a conglomerate, where you've had rocks swept together from a stream and then all mixed in. So we don't know, is it sedimentary, igneous, or impact?
Well, these were grains floating in a matrix, so it's not a big query if it was sedimentary.
We think it might be sedimentary. Now that's yeah.
Well,
all right,
this will run and run.
That particular piece there isn't showing it so much, but some of the clasts, the chunks that are in it, are very, very rounded. And one of the images that we've had from Curiosity, or we had loads of images from Curiosity, but one of them shows they look like water-worn pebbles that have been swept up together. One of the first images from Curiosity.
Very famous pictures of water-lane deposits.
Absolutely, and we think that this could be something like that.
Okay, so we know where Curiosity landed. It was right here on this bit of Mars. But of course, we don't know where your meteorite came from, which is the problem. But at least we have it in the lab.
Yeah, that's true.
Okay.
It's really interesting. So that's what I'm up to. What are you doing?
Well, I'm working on the Bepi Colombo European-Japanese mission to Mercury, and we're launching that in about a year's time. So that's going to be exciting because Mercury's a great place. But what's caught my attention in the news this week has been an object that was seen on its way out beyond the Earth, which was first taken to be a comet, then classified as an asteroid, and is now regarded as an interstellar visitor. The trajectory it's on is a hyperbola. It was travelling so fast when it came around the sun, it's not bound into orbit around the sun.
So it's like pretend this is the sun. It's sort of gone, woo, and it's going out like that.
It was quite silent, but that kind of trajectory. We've got an animation we can run showing its trajectory. So here it is coming in, that little thing there, from above the plane of the solar system, swept past the sun. It passed within about 20% of an astronomical unit of the Earth, I think, and it's outbound now like that. That's not a closed trajectory. It was travelling at 25 kilometres per second before it felt the sun's influence. Yeah. It's been given a weird name. It's been called 1I, I for interstellar, the first interstellar visitor.
All right.
/ Oumuamua.
Oumuamua
is a Hawaiian name. It was discovered at the observatory on Haleakala on Maui, so they gave it a Hawaiian name.
And does the Hawaiian name mean anything?
Oh, it means outward searching a long way away or something like that. There is a vague meaning to it. And it's a reddish body. It's red and like the Kuiper belt objects, but we really don't know its composition, rocky or icy. So, and we won't. It's on its way out now. Bye-bye.
So did anybody manage to... well, obviously people caught sight of it because we know its trajectory, but did anybody manage to get a spectrum other than to say it's reddy brown, or...?
It's 100 metres across. There's not a lot of light there. But it's a dark red object, but I think that's the best we're going to know, travelling fast. Yeah. So interesting, but there's never been an object like this seen before.
It's really interesting because we do have comets that come in at steep angles, and we think they've come from what we call the Oort cloud, which is this hypothetical construct which bounds the solar system.
Yeah, but their inbound and outbound legs of their trajectory are parallel because they're in the parabola, but this one was really diverging.
But the thing is, if here, I'm glad you brought this nice round object. So if this is our planetary system and the outside is the Oort cloud, all right, and you've got another planetary system here, you know, with its Oort cloud, and presumably the Oort clouds of the two systems will interact with each other.
Maybe.
What sort of a trajectory would a comet that comes from the Oort cloud of the planetary system down the road be like?
It depends what's knocked it out of a cloud in the first place, but it doesn't have to be sitting in an Oort cloud. It can be travelling through interstellar space like stars do.
Yeah. Fascinating.
Interesting to find this. Anyway, we should go on and start answering your questions now. We've had some in advance, and I will be keeping an eye on the widget, so please ask questions live. But to kick us off, Monica, there's a question which you're best placed to answer. This is from Alexandra Gemo, an S283 student who I think did the Moon's presentation before last. And Alexandra writes, I read on the NASA website that the hydrothermal chemistry inside Enceladus is going on at least 90 degrees centigrade. The amount of energy required is much more than what could be provided by decay of radioactive elements. So where Enceladus gets the power to remain active has always been a bit of a mystery. That's what it says on the NASA website. And she's saying, isn't that a bit weird? I thought it was well established that geologically active icy moons got their internal energy from tidal heating. Now, there has been a recent paper on this, so please tell us about it.
Right, so Alessandra, you're quite right when you say that the moons can get their internal energy from tidal heating, and the good example of that is Europa, which, well, actually the really, really good example of that is Io, because that's so close to Jupiter. It's like a squash ball, isn't it? Is the usual analogy for Io. It's sort of pulled and pushed by Jupiter, and the same happens to Europa to a limited extent. Now, the same will happen to Enceladus around Saturn, but it's a bit too far away for that to be the main reason why the tidal heating is happening. It's also in a tidal lock resonance with another of Saturn's moons, which is Dione, yeah. But again, that isn't enough energy to provide the pull and the push of the tidal heat. What's interesting, though, is it is a tidal heat. And there's a paper which Dave referred to, which came out in Nature Astronomy a couple of weeks ago. And that models Enceladus as having a rubbly core with a quite porous. So we know Enceladus's density is quite low. It's not low enough to be solid, just ice. So it's got to have some rock in there, but not a solid rocky core. So it looks as if it's a rubble pile in the middle. And in that rubble pile, fluid flows, and it's actually the pull and the push of the tides in those little fluid pores which provide the internal energy. Now, of course, if you want to read more about this, you can either go to the Nature Astronomy paper, or you could look at a blog site called The Conversation. And this is, just type in theconversation.com into Google or whatever, and you'll come up with this website. And it refreshes every day, and it has, well, its tagline is, what is it? Academic rigour with journalistic flair. So the idea is that academics write for The Conversation, and they have editors there which turn our dull prose into stuff that's readable. And
take it half the scientific words as well.
Anything that's got more than 5 syllables, they won't let you use. So Dave and I both write a lot for The Conversation, and we have a bit of banter about how many people have been reading our articles. So I wrote one last week about this tidal heating on Enceladus. So go away and read my article about Enceladus, and then I'll get lots more hits.
Yeah, you'll find links to my most recent Enceladus article on the moon's MOOC, but when its habitability was proven by the molecular hydrogen in the plume. It's a fascinating place.
It is.
I think what was as Andrew's point about what were NASA talking about, surely we knew about tidal heating. We knew that tidal heating would work. We didn't have a way to keep it persisting at the current rate for billions of years.
Yeah.
But this new flow model through the porous core
would do.
allows that
I mean,
to happen.
the thought, had been that maybe something had impacted Enceladus and sort of got a hydrothermal sort of circulation going, but the amount of heat that's radiated out of Enceladus would have caused that to freeze within a few million years. And it's clear this has been going on for quite some time. And also can go on for quite some time to come, which is interesting. They reckon that there is enough energy there, internal energy, to keep Enceladus ocean going for several more billion years.
Here's the plume visible now.
Right,
That's one of the views from Cassini of the plumes.
Great mission, Cassini. Really, really good. So anyway, that's... I hope that's answered your question, Alessandro. We've got another one, though, a related one from Andrew Austin, who's a S283 statement. And I just referred to impacts on Enceladus, and Andrew asks, has there been any evidence of impacts, or would the tidal heating or planetary resurfacing cover up any craters?
Well, there are plenty of craters on Enceladus, as maybe you could see on that view. But Andrew's also asking about Europa, isn't he? And he's referring to figures in the first S283 book. And he points out something on this very figure. Towards the bottom right of that, just in from the 4 o'clock position, there's a bright blob. And he's suggesting, isn't that a crater? Well, it is, and you'll read more about this crater when you get to the second book, Andrew. But on the figure on the same page as this one, there's some much smaller craters visible. So let's look at the next one. So here's figure 1.22. This is the broken up, chaotic surface of Europa with rafts of ice that have drifted apart. But there are 2 craters I can see on there, and we've got arrows on the next view. There you are. At those arrowheads, 2 small craters. Those craters are only a few hundred metres across. They must be quite young. So there are young craters on Europa. The surface can sustain craters at that size. It's not densely cratered. We know this is a fairly young surface, maybe only a few 100 million years old. It's certainly not billions of years old. Otherwise, that would be peppered much more fully with craters like that. But to go back to conclude with this, with a big crater that Andrew thought he could see on that global view, let's look at the remaining figure, which is here. It's from the second book in S283. The crater, Andrew, that you thought you saw is in the lower right. It's the same view before, but slightly different colours. It's blown up in the view on the right there. And you can see it's a crater that's many tens of kilometres across. It doesn't have a good crater shape. And that's because this crater was so big that it went right, the impact went right through the ice shell. It made a hole in it, but the ice shell was too weak to give good ramparts and so on. It's a trace of a crater. It's been given a name. It's called Pwyll. It's a Welsh name, Pwyll. And that's one of the few large craters which we can see on Enceladus, Europa.
Oh, Europa.
There's a couple of others which have similarly gone right through the ice shell, because the ice shell, for most of the time, is just a few tens of kilometres thick, and Europa is being tidally resurfaced all the time, broken up into rafts, melt-through processes going on, some plates sinking, and other areas of temporarily exposed ocean being refrozen. Of course, we know there's plumes on Europa as well, just as there are on Enceladus.
Yeah, but Enceladus is not as active on its surface as Europa is. Its plumes are all in one place around the South Pole, along these things that are called tiger stripes, which are sort of like ridges. But they're
plumes
not
coming out from Enceladus are more vigorous and more persistent than the plumes on Europa. But Europa's surface gets broken apart more dramatically. We think there's open ocean exposed, it'd be slush-covered ocean, but tracts of open ocean on Europa. No signs of that on Enceladus, just the cracks down to the internal ocean. But it's great, we've now got 2 moons with plumes erupting to space confirmed. Okay, now let's have a look for questions on the widget. We've got 2. Sandra's saying she was told last week that the Earth actually has 2 moons, according to QI. I've seen this on QI.
Yes, I've seen it on QI as well.
And Sandra said QI was wrong. I think you're right to say QI was wrong, Sandra. But what's your take on these temporary mini moons that the Earth picks up?
Well, I mean, are we talking about a moon or a satellite? Because we've got loads and loads of artificial satellites orbiting the Earth.
No, she's talking, I'm sure, about a natural object.
A natural object. But no, I don't know. I don't know any evidence for one that's persisting for a long time.
What you need to do, people, is read very short introduction to moons, or do the moons MOOC.
Oh, right.
And you will find out that now and then asteroids come by the Earth, do 2 or 3 loops, and then they're lost.
Sure.
They don't stay for very long.
Yeah, but I wouldn't call them a moon.
No, they're just temporary quasi-satellites. And there are also asteroids like Cruinia, which orbit the Sun in exactly 1 Earth year, and they have a relationship with the Earth, but they're going around the Sun, not going around the Earth. These horseshoe orbit things.
But I wouldn't have called either of those moons of...
No, but the QI elves do.
Yeah.
For those of you watching from abroad, it's a BBC comedy quiz show, but they're not real
they're not real
of the
moons,
Earth.
as I would have called them.
And Ben is asking, what's the latest news on the New Horizons mission to visit a Kuiper belt object?
Well, it's still going. It hasn't got there yet. It's going to take a fair few years, but...
It went past Pluto in July 2 years ago.
2015?
Now, yes, 2 years ago. And around about the 1st of January 2019, it's going to get to its next target.
Oh, it's as soon as that,
It's as soon as that. It's a year and a bit time. It'll take a while to get all the data back.
I thought it was going to take about 6 years to get to, but
and
I bow to you.
It's an object which might be a double object or might have a moon. There's evidence it occulted a star, and its shape is looking very elongated, maybe double-lobed, maybe even almost a contact binary. So it'll be a fascinating object to see. It's only about 40 kilometres across, but it might be double.
Oh, right, okay.
And the spacecraft is healthy.
Yeah, good. Because they've found a lot of the observations that have been made of the Kuiper belt object seems to imply that a lot of them are doubled binaries.
Yes, and there are plenty of double asteroids as well.
Yeah,
it is
yeah.
a dynamical problem to get these
Yeah,
objects.
yeah.
You can't capture things very easily.
Yeah.
Your comet is a two-lobed thing, and there's a theory it's two objects that came together and stuck.
Yeah, well, I mean, the
Rosetta comet.
Those two
67P.
lobes. They look as if they have been two separate. Oh, there we go. So the two lobes. Thank you. It looks as if they were separate objects, but they're so similar in their chemistry and stuff that it's probable they were one object that was broken up and then they reaggregated. But yeah, interesting.
Okay, let's have some more questions that came ahead of time. Here's one from a MOOC learner, Mike Wilson. Mike says, why do meteorites end up on the moons when the planets have a much greater gravitational attraction?
Well, I think my answer to that has to be, Mike, they don't. I mean, we have lots of meteorites on the Earth, and we have some meteorites on the moons. But we've got meteorites on Mars. We know that. We've had them that come from Mars, but we also have seen from Curiosity and Opportunity that there are meteorites on Mars. So they don't. They just come into the general vicinity of the planet, whichever planet it is. By far the biggest number of asteroids miss the Earth, miss the Moon, and they don't land anywhere, or they get sucked into the sun. But there is no gravitational focusing from the Earth. I mean, this is something that has been looked at in terms of trying to decide, okay, as the Earth is going in its orbit around the sun, are we getting any sort of gravitational focusing? So more asteroids are sucked in towards the poles, or do more fall around the equator, or do more fall, in the morning? And there is a very, very slight preponderance of asteroids falling on the Earth in the afternoon, so in the tail part of the orbit around the sun. But there is no gravitational focusing to get meteorites onto a planet or onto its moon either, because these things are just travelling so fast and they just hit the thing that they hit first.
Yeah, I mean, travelling at tens of kilometres a second, you're not close to the Earth for long enough to be deflected towards the Earth, hardly.
You're
just going to go straight on into the Earth.
Yeah.
And the Earth would have as many craters on it as the Moon does, except the Earth is an active body with lots of resurfacing processes, and the Moon preserves the record.
That's it. So, I mean, if you're just going on the fact that we don't see the craters on the Earth, it's because the Earth's covered with a lot of sea, and the Earth's, got plate tectonics, which is taking away the older material. So, and we have soil and vegetation and all these sorts of things. So we just don't see the majority of the craters that we have on the Earth. But if all that was stripped away, the Earth would look like the Moon, peppered.
Yeah.
Right, okay. Dave, here's one from you, from one of our MOOC learners, Carmela Cox. Last week we learnt that Saturn's shepherd moons help to stabilise the edge of its rings. What would the rings look like if those moons weren't there?
Okay, as Carmela says, the shepherd moons are small moons that are just outside or just in between some of Saturn's rings, and they do keep the rings tight. And I guess if they weren't there, the edges of the rings would be fuzzy. What occurred to me looking at this question before time was that actually we don't know how the shepherd moons form. The shepherd moons might actually form from ring material. There is this little clot visible in the outer edge of Saturn's A-ring. Yeah,
you get these little propeller shapes, don't you? Or is that something
different?
Well,
there are propellers which are sort of banded things, but I'm thinking of a little object that's been nicknamed Peggy, that's been seen in the outer part of Saturn. That might, it's not been spatially resolved, but there's a little object there which might be growing within the rings. Maybe the rings grow their own shepherd moons, because if you look at the shepherd moons that have been seen in high resolution, they've got little flanges around their equator. They're very curiously shaped things. So maybe the rings grow their own shepherd moons. We don't know this, but without the shepherd moons, the edges of the rings would be fuzzy.
Not as well. Right, well, I'm holding this book back up again because, who was it? Patricia says, what was the Moon's book you held up briefly and said, oh, look at? She didn't catch it. Well, it's called Moons, a very short introduction, and it's by some charlatan called David A. Rothery, produced by Oxford University Press. I don't know whether we're allowed to do adverts.
No, we're not. You can find a link to it on my Future Learn profile.
But there it is. It's Moon's, a very short introduction.
Thank you, Patricia.
This is,
so that was a live question.
Is this Patricia, Rothery Jukes, perhaps, your niece? Or?
Monica, we've had a question from Malcolm Longridge, an S283 student.
Okay.
Who is saying, if humans wanted to live on the Moon or Mars for several years or permanently, assuming no other limiting factors, would there be any physiological problems associated with long-term exposure to lower than Earth gravity?
Yes, that's a really interesting question, because there's often a lot talked about the psychological problems of being in a small group of people on a planet, but the physiological questions are the sort of problems, are the sort of things that the space shuttle astronauts experience. Now, they're in a much lower gravity than you would actually have on the surface of Mars. But even so, at the moment we're built we're designed, as it were, for 1G, all right? Now, as soon as you go into lower gravity than that, then your internal organs aren't reacting in the same way as they do. So your heart, which at the moment is pumping blood, and it has to pump blood upwards, assuming you're standing upright, it has to pump blood upwards to your head and downwards, and the blood has to circulate. Now, would the pump not have to act so hard, in low gravity? I'm not sure. There's other things like your bones. You won't have to force yourself so hard when you're walking, because you'd be able to bound and leap and this sort of thing. Now that means that you actually won't be using the muscles that we have. So your muscles might wither. There'll be problems with, as I say, the bones, because the chemistry of what your blood's doing and how your bones need to be strengthened to support everything which has the weight of a 1G environment. It's just like, right, okay, so we don't need to have bones of such density. So your bones will get less dense. Now, presumably, if you're going to stay on Mars or the Moon, and I'm not talking about radiation or anything like that, because that's also a problem, but if you're going to stay there and you're going to breed and you're going to build a colony, then gradually evolution will kick in, and humanoids that are more suited for that sort of low gravity environment will eventually evolve. But if you're going to live there for a year and then come back to Earth, then you'll be in real trouble.
Yeah, thank you,
Does that make
Monica.
sense?
Yeah.
Good. Right.
We've been getting some live questions here, which I'd just like to deal with. Jacob Bramley has been reading these pictures on the wall behind me. These are a couple of blow-ups of our Moon Trumps cards, which if you're studying Moon Trumps, studying the Moon's MOOC, you can get to play. But if you're not, just go to Open Learn and search for Moon Trumps. You can play the game online. It's like Top Trumps, but similar, and you can buy packs of cards if you want. But Jacob's point is, he has read it correctly, but it says on there that Europa has a 50% potential for life, and Enceladus has a 30% potential for life in this game. You can play against the computer, or if you get the cards, you can play against your children. And you
let them beat you.
I came up with these numbers.
You mean you made them up?
I made them up, and when we made these numbers up 4 years ago, I thought Europa had a greater potential for life than Enceladus. Now we've got molecular hydrogen in Enceladus's plume. I'd perhaps put Enceladus as having higher potential for life.
What's the significance of the hydrogen?
We've got a complete metabolic pathway inside Enceladus with a hydrothermal reaction between water and rock, dissolved silica, we've got methane. The molecular hydrogen shows that there could be methanogens taking the hydrogen, bonding it with carbon to produce the methane. We've got proof of everything going on inside Enceladus except the microbes living off the chemistry. We don't know that there's such complex chemistry on Europa, though I think it's likely.
Well, I mean, the start of it is the hydrothermal, the serpentinization reaction, because we're fairly certain we've got those rocks, and we don't know about the rocks, whether there are those rocks there
inside Europa.
But we do on Enceladus.
Yeah, but the tidal heating inside Europa ought to be greater.
Ought to be.
But you can argue it. But Jacob is saying that 30%, 50% is a bit optimistic, isn't it? Well, perhaps it is. We see, what we don't know is how easy it is to get life started. There are habitable environments inside Europa and Enceladus. Most people would not doubt that. But whether they are inhabited has life got kicked off? That's just what we don't know. And that is a very, very big question.
Yeah. And if it's there, you know, has it evolved, or is it really just bacterial? I mean, one of the analogies that are made for Europa is that on the ocean floor there might be hydrothermal vents like we have on the Earth, but around the hydrothermal vents on the Earth we've got crabs and tube worms and all sorts of stuff, and they are quite they're much higher forms of life than just bacteria. Could we have those on Enceladus?
Well, this is why knowing that Enceladus can be tidally heated over a time span of many billions of years gives potential for life to have started billions of years ago and to have had time to evolve along the way.
Yes, but I thought Enceladus had only been there for 180 million years.
Well, it says so in one of my articles on the conversation.
It does, and I believe I referred to it.
But that is not definitely the case. If it's been there for 4 billion years, life could have had a chance to evolve a long way. Yeah. But it'd be a pretty impoverished ecosystem down there because there's not a lot of nutrients. We're running out of time. There's a question here I'd like us to answer. Alan Townsend, as our solar system moves around the galaxy, are we likely to pick up stray planets? Well, we don't know how many stray planets there are, but if we do encounter one, the relative speed is likely to be so fast, it's going to do what Oumuamua did and just whiz round the sun in a hyperbola and be flung off again. Very hard to capture something that you encounter with your sort of the speed that you're travelling through the galaxy. Do you concur, Professor Grady?
I do concur, Professor Rothery, indeed.
But it's been suggested that there are starless planets wandering around.
Yeah. Just sort of bumbling around. Aren't they mainly brown? No, they're not brown dwarfs, are they?
Brown dwarfs are almost... But they're very hard to capture something, basically, because you've got to match velocities with it.
And we've got no idea how many there are out there, because they're not stars, they're planets. And so they only... they don't shine, they only reflect light, and so we've got no clue how many there might be.
There have been 1 or 2 gravitational microlensing detections of possible stray planets, but we don't know. So we don't know how many there are, but I think definitely very, very hard to be captured. More likely just to whiz round.
Yeah.
We are running out of time. Before we get to the very final question, let's have one more question that came in advance.
We're going to do Barbara Johnson of S283, who asks, what discoveries do you think or hope might be made in the next 10 years? Now, the idea is, you ask me that. That puts me on the spot, but now I've asked you, so I'm putting you on the spot.
Well, in about 8 years from now, we'll have the wonderful Bepi Colombo mission in orbit around Mercury with a big suite of instruments and with 2 spacecraft. And we're going to find out about the volatile richness of Mercury, because Mercury is a strange place. We know from NASA's Messenger mission there have been explosive volcanic eruptions, so there's something coming with the magma to the surface that turns to gas that drives an explosive eruption. There's sulfur everywhere across the surface. We think as sulfides, not elemental sulfur. There's patches of surface that look moth-eaten. There's something that's just volatilizing and going away to space, leaving steep-sided, flat-bottomed depressions just in certain areas. And there's lots of chlorine and carbon and potassium. and things that shouldn't be there in high abundance that close to the sun. We want to pin these down rather more to understand how Mercury was made and what the heck it is doing so close to the sun now if it was made further away from the sun, as is beginning to seem likely. So the discoveries I'm looking forward to are ones I hope to play a role in with Bepi Colombo, because we've got a British-built X-ray spectrometer which will hopefully map carbon. Difficult call with X-rays, but we can just about get down to the carbon energies.
Okay. Well, of course, carbon is something that I'm really interested in, but I'm hoping for things that, you know, from on the other side, you know, because we've got a whole new suite of missions going to Mars, Mars 2020, which is a NASA mission, which will send something like Curiosity again. But there's also a joint mission between the European Space Agency and the Russian Space Agency called ExoMars. And on ExoMars, there's going to be a static platform as well as a rover. But on the static platform, there is going to be a mass spectrometer, just like the one that went to 67P, which is being built even as we speak. And plus also there's going to be an ESA Russian mission to the moon with another of these mass spectrometers on. You know, if you're going to build one, you might as well build three. And so we're hoping that that's going to go to the south pole of the moon and look at the water, look for ice in the permanently shaded craters.
When and how are we going to discover if any of these habitable places do have inhabitants in the form of microbes?
Don't know. No idea. I mean, you've got to be so sure that you know what you're going to be looking for. You've got to be so sure that any strange signature you find in chemistry or whatever can only be explained by something that's alive. And there'll always be some, you know, doubt. And until you bring a rock back from Mars and you analyse it in the laboratory and you are utterly certain, you know, or you see, you know, you bring your rock back from Mars and something with wings and two legs and an antenna on its head crawls out of the rock so you can see the Martian life, then people might be convinced.
And Mars sample return is always 10 or 15 years away.
2030, I reckon. 2030.
Okay. I'll take one more question because we do have to finish. John Reed says Venus is an example of a runaway greenhouse effect. It's got a dense atmosphere, traps a lot of sunlight because a lot of it is CO2. Why is there so little probe interest?
Smelly.
When there have been... well, there was the European Venus Express recently, studied the atmosphere, and prior to that it was Magellan. If you've ever seen radar images of the surface, that'll be from NASA's Magellan, which was 20 odd years ago.
Oh, more than that.
Yeah. There was a meeting going on last week, colleagues of mine were at trying to boost Venus up the agenda. It's a difficult place to land on because it's so hot that your electronics can't work at that temperature.
I mean, there's only been one lander that worked, and that was a Russian lander from the 1970s, was it?
4 landers. We've got pictures from 2 or 3 places.
Yes, but they only lasted for less than a minute,
Absolutely.
something like that.
We've got
because
1 or 2 pictures.
It's like 400 or 500 degrees on the surface, lots of sulfur.
It's hotter than Mercury.
Hotter, yeah. It's like so hot that if you were walking on it, the soles of your shoes would melt. And it's like, well, you know, who cares?
Yeah. No, it's
important. It's very important. It's a very important part of the jigsaw, which is Mercury, Venus, Earth, Mars, giant planets and their satellites. How have all these really different objects been put together and evolved from the same cloud of gas and dust?
Yeah, well, Venus ought to be Earth's twin. It's almost the same size, mass and density.
But it's got no magnetic field.
No. Well, it might be just because it's not rotating very fast.
I was going to say, doesn't it go around the sun the wrong way as well?
No, all planets go around the sun the same way. It's rotating its axis retrograde very slowly.
Yeah.
So what's happened to its magnetic field, yet it's still held onto its dense atmosphere. And the water has escaped because it got so hot and it got photo-dissociated in the upper atmosphere, and the hydrogen's gone to space and the water's oxidised the rocks. but you've got no plate tectonics to resurface the
Recycle.
planet in the same way, with recycling going on. It behaves very, very differently. But there is an interesting tectonic and volcanic story on the surface, but it's not arranged like it is on the Earth. So we would love to know. It should be the most similar planet to the Earth, and it isn't.
It's the same size, and it's so different.
Yeah. There should be more interest, but with all the other low-hanging fruit, where you can get results back with greater guarantee of success, it's a hard nut to crack, really. So I can mix my metaphors.
Yeah, especially as you go to a comet. It's taken so many years to plan that mission. You go there, you find fantastic results. Immediately, everybody wants to go back to another comet. You send us a spacecraft to Saturn, like Cassini. You find fantastic results. People want to go back to Cassini. We had a mission to Jupiter. When was Galileo?
Galileo ended
1995, something like that.
Till 01 or something.
Yeah, something like that. And it's taken until now to get the next mission to Jupiter, which is JUICE. And that's...
No, there's Juno around Jupiter right now, not imaging much, but it's discovered stuff about the core being fluffy.
Right. Oh, well, sorry, I was thinking of stuff that we are involved in, or
Okay.
we, Europe, being involved in, and that's JUICE. That's the next big Jupiter mission.
Colleagues at Leicester are involved in
Juno.
and the
All right.
magnetometer.
Okay.
So
Yeah.
actually Britain has a very big, we hit above our weight, punch above our weight in planetary science and
Right.
space missions.
Yeah, I guess you're right. But it takes a long time, and it's like, well, Venus just seems to lose out. I don't know why, you know.
Its time will come.
Its time will come.
And
But ours has gone.
our time has gone. Yes, perfect. Thank you, everybody, for your participation and for all the questions. Samantha, there will be a recording of this on YouTube, maybe tomorrow, maybe the day after. Recording on Stadium, the system we're viewing on now, will be there within the hour. But there'll be a YouTube version up there available for anybody in the world to find. If you can find the previous 7 recordings we've done of this, or many there are, there will be, this one will be in the same place. Open University, Planets and Moons, you'll find it. Thank you, everybody. Thank you, Monica.
My pleasure.
Thank you to Kate and Ben in the background, keeping this running smoothly. Enjoy the rest of the Moons MOOC. Enjoy S283. We'll have another of these Planets and Moons chats in early March, and I will have other guests then.
And don't forget to sign up for the Orion MOOC.
Or read the conversation.
Or read the conversation.
Good night, everybody.
Bye-bye.